video, we're going to update you on the latest inspection and monitoring to help you have safer and more reliable bridges. The challenge of managing hidden critical elements has never been higher, with hidden defects leading to bridge closures and, in some cases worse, making headlines worldwide. Some of the elements more commonly at risk include post-tension tendons and cables, welds and cast iron structures, as well as concrete joints. Bridge engineers now have the opportunity to significantly improve the effectiveness of asset management using targeted NDT inspection and structural health monitoring with solutions specifically designed for hidden elements that confirm both their condition and, in some instances, their construction without the need for intrusive and destructive inspections. Concern about post-tension bridges persists. The A52 bridge in Nottingham, England, making headlines in early 2020, showing that integrity issues like those found at Hammersmith Flyover in London and the Morandi Bridge in Genoa still exist. Improvements in non-destructive testing now allows non-invasive examination of external ducts, voids and tendon corrosion using digital radiography imaging. If there is access to the anchorages, the ends of tendon wires can be scanned for corrosion and wire break, with flaws detected up to 2 meters away from the anchor head. Long-term acoustic emission monitoring, like that deployed at Clifton Bridge in Nottingham, England, is effective for both internal and external post-tension systems, detecting and triangulating the location of wire breaks, enabling highlighting of areas of concern for further inspection, or in the absence of wire break, providing reassurance about the condition of the structure. Steel fatigue of both road and rail bridges continues due to increasing asset age as vehicle loads and numbers increase. Fatigue problems commonly manifest themselves as stiffness on the flanges and webs, as well as on orthotropic decks. The use of high sample rate strain gauge based monitoring, often deployed over short periods of time, is a very effective tool to determine the actual stresses under real-life service loading. The data collected from this model enables the validation of digital twins for fatigue life prediction and future repair planning. Practical NDT testing on site, using modern eddy current methods, enables the accurate detection of surface breaking cracks, sometimes only millimeters of length, underneath paint. Fully or semi-autonomous NDT now enables significant lengths of welds to be quickly assessed on site. More local investigations, such as the use of advanced phased array ultrasonics, enables the investigation of complex weld geometries for cracks, often located around the heat-affected zone. These NDT and monitoring techniques can also be used effectively on heritage structures constructed of early steel, cast and wrought iron. A good example is the Hammersmith Suspension Bridge, which has utilised a range of different advanced NDT, acoustic emission and strain gauge based SHM to detect and manage defects during initial investigations, as well as its ongoing rehabilitation. Suspension bridge cable health can be well managed with the use of dehumidification systems and acoustic monitoring. Smaller diameter cables, using multi-strand, rope or locked coil, can be equally vulnerable, however, as the dramatic failure of the Arecibo Space Telescope and the Nanfango Bridge in Taiwan has shown. Advances in data processing and distributed structural health can forewarn of problems and risks in both new and existing structures by detecting and measuring structural vibrations under wind and traffic loading, monitoring environmental conditions that may indicate the parameters that allow corrosion to occur, and acoustic emission used to detect wire break in all of these different types of cable. Thank you for watching. I trust that this has been of interest, and if you'd like to learn more, please reach out. Thank you.